We're the Techno Vikings, and we're making the self-scoring steel-tip dartboard. I'm Craig Carr.
I'm Ming-chin.
I'm Chase Wright.
Brandon Smith.
And we're the Techno Vikings. Next slide, please. So something we're going to go over today is just a quick intro, problem statement, objectives, the whole system architecture and breakdown, by the modules, deliverables, schedule, budget breakdown, and then finally a summary. And then you'll have time for questions at the end. So quick problem statement. Our client was Doug Kiefner. He was the president of the Low Country Dart League. He went MIA, no idea what happened to him about October. So if you want a dartboard, let us know. Our task was to reliably track the score of two players in a game of steel-tip dartboards. And so the problem we identified was we need to attract new players, as well as keeping it simple, stupid for people that may be inebriated or just don't know how to play the game of darts. Solution proposed: self-scoring steel-tip dartboard. So our objectives for our dart detection system, this was given to us by the client, sort of. So the dart detection system would locate the position of dart within 1 second of a dart striking, and then also sequential hits from darts. So it won't just stop at one dart, it will wait for 3. As well as maintain an accurate score. The display unit display the player's scores, as well as whenever it decrements, which turn it is, ability to reset and take care of missed throws. The controller should accurately calculate current score, adjust for bus system, ability to reset, again process missed throws, and then for the power source, needs to adequately power the whole system with a rechargeable battery. So
So this is the big picture overview of the architecture. So we have a 12 volt rechargeable battery power source. It's going to feed into the 5 volt controller and the dart detection system, which has a couple components, which requires 10 volts and 5 volts. And then also we have the display unit hooked up to the controller, which will hold 5 volts from there.
this is kind of more on this, how the modules are broken down. So we'll have module 1 is the dart detection system. Module 2 is the microcontroller. Module 3 is display, and module 4 is the power supply. And that's kind of how it's broken down, how they all work together. So this is the original design from last semester, plus 1 LCD, and this is how it's turned out at its present state. This picture was taken a day before this was turned in. So it stayed pretty similar as far as the physical architectural layout, but it gets pretty hairy as you flip it over. Next. So my module is power supply and distribution. Again, we have a 12 volt battery. It's rechargeable, supplying multiple different voltages. So the biggest thing that I had to do was drop it down from 12 volts to 5 volts for the microcontrollers, 10 volts for the light-dependent resistors, and then again 5 volts for the laser dot diodes, which I'll get into a little bit of that later as far as what we did with those. This is kind of the process of what I was doing. I had to solder this printed circuit board. I ended up using, I believe, 8 LM317s, and then this little voltage regulator that Mr. Knapp gave me to supply the 10 volts to the light-dependent resistors. And then this is kind of how it's going on the back. So there's that printed circuit board that I've got up there, the finished product, and you can see those red wires going to the different microcontrollers and supplying power. You can see that the FPGAs are on, so it's providing good power, and it sort of works.
Alright, so we'll go into the dart detection system. So it's got, as you can see, a bunch of pieces and parts. The main bulk of it consists of 160 LDRs, supplied by 10 volts. We have 13 modified lasers, which I'll talk about in a minute. While they're modified, supplied by 5 volts. We have a total of 5 FPGAs on the back, which their job is to monitor those LDRs. This is kind of a scaled down 4x4 layout of the LDRs. So we've got a 10 volt supply feeding to all the LDRs, which are just varying in resistance based on the intensity of light hitting them. And then downstream of those is a 1 k ohm resistor for each of those. And then tapped off in between those is the output. Is basically, it goes to the FPGA channels, which are configured as multiplexers. And it sends the status of the voltage at this point. So the dart blocks, if the dart blocks the laser being shined on the LDR, it's going to change the voltage corresponding to whether or not there's a dart there, and it will send that information on to the FPGAs, which are displayed right here. Like I said, 5 FPGAs, 4 of them are the CMOD A735Ts, and then one of them is a CMOD S7. And so these are schematics for the FPGAs. This one right here is the A735T, and this is kind of how we have it configured. So it's pretty much written as a multiplexer, a 37 to 1 multiplexer. We have the C-select lines coming in here, which will be controlled by the Raspberry Pi, the controller module, and continuously cycle through each one of these. So shown here is one of them, but there's going to be 4. There are 4 of these on the back of the board. Each one of these corresponds to one of the LDRs, and this is the output that goes to the Raspberry Pi to tell us whether or not there is a dart blocking each one of these channels. Yep. So, and this is a very similar schematic. This one is the CMOD S7. Has less I/O pins, but we needed it to cover up a little piece of the bottom corner of the board that would be covered by the 4 other FPGAs, and we had some of these left over. So that's how it's configured. We don't use all the channels, all the I/O pins on that, and we ended up just having one of these, and it is a 12 to 1 So let's talk about changes from the original design. So kind of a side view here. So that bar at the top right there, those are all, can't really see them in this shot, but those are all the LDRs lined up. And there's 80 of them on this, let's call it the x-axis, and another 80 on this y-axis. And originally we had 160 lasers, and we thought it was a great idea to line up 160 lasers and shine one, get all of them perfectly parallel to one another, and shine directly across and hit one and only one of those LDRs. And that was a terrible idea because we got like 10 of them mounted, and maybe, yeah, well, yeah, I got like 10 of them mounted, and you put them right beside each other, buttoned up against each other, and their spread just looks like this, right? They're all over the place. They're inconsistent between each layer. So we worked around that, and what we did was so you can see the laser there. So we took the lens off of each one of them. We just unscrewed the little barrel, and it's no longer a laser at that point. It's an LED. It's a point source. And then what we did, the idea was we have these biconvex lenses, and if you put the laser right at the focal length of these biconvex lens, it takes this spread of light. If you get it just right, it perfectly collimates it. The width, well, slightly less than the width of the actual lens, instead of straight down, and it smoothly covers several of those LDRs rather than just one, like one laser. So that's one of the changes we went through, and we also miscounted the number of bits you need to count to 36 in binary. So that's why we had this extra CMOD S7 laying around, and we were able to use that.
Going into the controller module, sort of viewing the controller as both the brains of the operation as well as the bridge between hardware and software. What we wanted to do with this, we're using a Raspberry Pi Model 3B. And so what we're using the Raspberry for is basically having, from a software standpoint, is having the dart detection, scan sensors, next button, calculating score, displaying the score, and the next player. This all gets broken down into the hardware side of the dart detection circuit, taking care of the hardware components for that, for the dart detection as well as the scan sensors versus the display circuit, which helps with the next button and displaying the score as well as showing the difference between the next two players. From a hardware standpoint, the display unit takes about 6 pins. The detection circuit itself takes 16 pins, 4 for each FPGA, and then 4 pins for power unit. And then for coding, we are using Python. We felt that that would be the easiest programming language for both of us on the software side, and we are using Thani, which is a Python IDE. I'm kind of known as the flowchart guy that kind of screwed up his first flowcharts and then I had to go back and redo them. So with that being said, these are the modified flowcharts overall.
Okay, as for the display unit, at first we are trying to use 2 LCDs in our design, but we found that the SDA pin and SCL pin there is only one SDA pin and SCL pins on the Raspberry Pi, which is the I2C signal. So we use the one LCD to display 2 lines. First line for player 1 and second line for player 2. And 2 buttons for the double gain. One is the reset button. So when a player, when they mess up the player's round, they can press the restart button to reset the score to 501 and make the player make the round to be the player 1's first start. Okay, as for the next player button, when players throw the darts out of the detection area, we can use the next player button to switch the player. Yeah.
Alright, quick on the deliverables. So, still working on it. We hope to deliver a working system that will automatically calculate your this score of your darts. This is our schedule. This is some of the things that we completed over the semester. Right now we're doing Happy CEEDS Day, and then our final project paper is due on Monday. Budget breakdown, I believe, we're probably over budget, but if you consider all the random pieces that we've gotten from Mr. Knapp, his generous soul, but if you consider all the hours that we put in, we're about 62 grand if we were an actual engineers. All right. Summary, so all the highlighted parts or the bolded parts is what works. Now, not all of it works together, so take that into consideration, but that's good. Any questions? Yeah. Any questions?
I2C.
I2C.
You said you only had one connection on the Pi.
Yes.
But I thought I2C was a bus that you could hook multiple.
Yeah, but we have to connect to SDA and SCL, which only have one on the Raspberry Pi 3B. If we want
It's a
to
bus.
connect,
It's a bus.
plus,
It's like USB, you can hook multiple things to the same pin.
Just trying to keep it simple, sir.
I saw one of those flow charts that had E on there.
No,
No,
you didn't.
not there.
Not there.
Not there.
You must have been looking at the other guy's project.
Yeah.
Jeez.
I'm lying.
Next question, yes, sir.
What other approaches did you consider when first developing
Oh,
this in terms
how much
of?
time do you have? Our like day one consideration, pressure sensors. That was shot down real quick because we're using steel tip dartboards, and to break down you can't break down a steel tip dartboard like you can a soft tip. They're made out of plastic, pretty cheap, or you can get pretty cheap materials. But steel tip dartboards are thick, sometimes like horsehair. We have cork, I believe, which is a little bit cheaper material. But then you risk punching through. We also considered using the same kind of thing, using IR sensors, and then pretty much everything we ran into was resolution. If you want to get in that.
Yeah, we also considered like an ultrasonic type thing. We were a little concerned with the accuracy when we're talking, it's not a very big space, so we were concerned with that a little bit. So we kind of left that on the table and ended up going with the lasers.
Another option was cameras. which was definitely a viable option. It can be very accurate, have good resolution. I believe we decided that that would have been more of a computer project rather than an integrated electrical and computer project. And this looked fun.
Was it?
Yes, sir, it actually was. Still is. Good luck.
Who chose the font size?
Next question. What was the hardest part?
Yeah.
What's the hardest part? I knew that question was coming, right? Okay. Hardest part for me, probably like every time I tried to implement something or integrate something. I'm not going to say the integration was the hardest part. Of course it was, we all know that. But just like the continuous problems that would arise, and then me racking my brain trying to figure out how to fix every single level. And I know everybody, all of y'all could probably say the same thing. It seemed a very delicate system.
Okay, the hardest part for me is to combine all the codes together because we are using a different library or different methods to do the code. And so when we are trying to combine it together, we have to redefine the object we used and then use different methods to plug it in and then make the main loop to go over successfully.
Probably the hardest one for me was finding the communication between the Raspberry Pi as well as the FPGA outputs. I think for a good week and a half, especially this past week and a half, has been really difficult trying to wrap my brain around trying different tests as well as importing different libraries to see which one would actually stick. We got together and I talked to both Carr and Smith, figuring out whether or not it was a hardware or software issue. We flipped the board over, we were double checking wires and everything, realized we might have been missing a wire. But overall, after that, it all just became part of the programming process that we're going through right now.
The hardest part, as far as I encountered, was the construction. There's over like 350 solder connections on the back of that thing. That took a while. And then those lenses, so that worked really well on paper, but each one of those lenses are different than the other, and each one of those lasers are different than the other, and they don't have a focal point, it's more of a focal area, and they don't produce perfectly collimated light. So trying to hand set each one of those, I don't know if you looked at the board, it looks very staggered, and they look like they were placed there on accident, but they weren't. They were very precisely moved to get the best version of what should have happened on the actual board. Yes.
So, when you look at the back of this, it's obviously not robust, right? I mean, it's so. Could you move to ribbon cables? Could you move to something that you could have a piece of machinery that goes and clamps down, and you've now connected all of these wires together and make it more modular that way?
So something I was talking about whenever people were coming through earlier is serializing, and you can do that with both the LDRs and the lasers. So yes, you could make it much more simple, and we looked into that, but we have a budget, and so like we were originally going to use the like a rail of lasers. We found someone that could make it for us, but it was going to be ridiculously expensive. So it just came down to cost. Yes, there is a way, and we could have like printed circuit board a lot of it. We didn't. Not a lot of work.
Yeah, on that we have 5 FPGAs on the back of the thing. Talking to Dr. Haynes this morning, so those FPGAs have a lot of bells and whistles on the actual board that are not necessary for the application. We can definitely get just the FPGA chip, do a little bit of customization on it, and we would only need one FPGA. And the actual chip itself is fairly cheap, less than, it's on the order of like $50 for. Could do the job of all 5 of those FPGAs with a little bit of customization.